In this video, we will derive the formulas related to center of mass for a planar lamina of constant density, given that our region lies between two curves. Last time we had the region lying between two functions of x. This time we've got a region that lies between two functions of y. So our x's are going from g of y on the left to f of y on the right. So this is our left function, and this is our right function. And remember, the way we're looking at it left to right, we're just, the right ones are well, it's obvious, this is on the right and that's on the left. But whenever we do our integration, f of y is the one with the larger x values, and g of y is the one with the smaller x values. And this, at the same time, y is in between two constants, c and d. So that's our region. One other thing that I wanted to point out in this section is, or before we get started, is something I didn't mention in the last video. In this lesson in our textbook, they're using planar laminas of constant density. So that density does not depend on x or y or both, although theoretically it could. If the density is constant, then the center of mass doesn't depend on that density at all, because the mass is evenly distributed throughout the entire region. Given that, we don't need to call it a center of mass. We have another term for it. It's called a centroid. The centroid of a region is just a special name for the center of mass of a region that has constant density. It depends entirely on the shape of the region, and it has nothing to do with the distribution of mass, because the mass is evenly distributed. Okay, so with that in mind, I want to derive the formulas for the center of mass of this, also known as the centroid of a region that looks like this, and then we'll apply them in a problem. Okay, so we do the same thing that we always do. I sketch my region. And we're going to subdivide the region into n rectangles. And then this is pretty cool. If you want to find the moment of the region about the x-axis or y-axis, all you have to do is find the moment of one of these rectangles and then add them up. Just like we did when we were looking at moments about the origin, or moments about the x-axis or y-axis with just our point masses. The same principle holds even when we've got infinitely many points in between two curves and two other lines. I think that's pretty cool. So we subdivide into n rectangles, we look at the ith rectangle, and we find the moment of that rectangle about the x-axis and the y-axis. Now be careful here, it's not exactly what you think. The moment of that rectangle about the x-axis is still mass times distance from the x-axis, and mass is going to be density, that's mass per unit area, times the area of that rectangle, times the distance to the x-axis. Remember that you're going to the x-axis next. Density is given, it's rho. The area is found a little differently this time. Because we were in between two horizontal lines, y equals c and y equals d, and we were between two functions of x on the left and x on the right, it made more sense to draw our rectangles this way. Because when I draw my rectangles this way, I've always got the same right function and the same left function. So the area of this rectangle is just, let's say we're going to pick out a particular y value on that interval, y sub I. We're going to evaluate the function there and this function there at y sub I. Well, this value of x is f of y sub I. So we're taking the x value on the right, and we're evaluating it at y sub I, and we're subtracting the x value on the left. So this is x right minus x left. Oops, g of y sub I. And we're multiplying that by delta y this time. Okay, so this is density times area. That hasn't changed. But now the distance to the x-axis is this distance. Now remember, if this is y sub I, like if that was y equals 5, the distance from here to here would just be 5. It's just going to be the y value. That vertical distance is the top y value minus the bottom y value. The top y value is just y, the bottom y value is just 0, so the distance is y sub I. So we're seeing that when we take a moment about the x-axis this time, it looks similar to the moment of the other one about the y-axis. We have rho, we can factor that out because it's constant, and now I've got a y times the right function minus the left function, dy, and we're going to integrate from this y value to this y value, so that's y equals c to y equals d. Now I might prefer, especially in this case, to remind myself this is x on the right as a function of y minus x on the left as a function of y times dy. That's what we're trying to do. That's the moment about the x-axis for this region. Similarly, the moment about the y-axis for that particular piece is mass times distance to the y-axis. So the mass is just our density times the area, because our density is mass per unit area. And the area of this rectangle, again, is right function minus left function. So f of y minus g of y times the width of that rectangle, which is delta y. This whole piece is my area. And this distance here, be careful, it's not the x value. It's the average x value. X is going between this function on the left and this function on the right. So it's the average of this one and this one. To find the average of two x values, I just add them together and divide by 2. So this distance here, the distance to the y-axis, is the average x value. So it's 1/2 of f of y plus g of y. That's my distance. And I can simplify this, put all these pieces together. You've got rho over 2. F plus g times f minus g is f of y squared minus g of y squared. You can simplify that if you want to. I do when I write down the formulas, but pretty much every time I draw my own picture and calculate these using the picture. So you can go straight to this if you prefer, but you don't have to. I think it makes more sense if I draw a picture. And then the moment about the y-axis is I add all of these up for all n rectangles and take the limit as the number of rectangles goes to infinity. And we get this. Rho over 2 times the integral of f of y squared minus g of y squared dy, and we're integrating from c to d. Now f of y is the x on the right. It's your right function. And g of y is x on the left as a function of y. So those are our moments. Now if I want to find the mass of the lamina, well, that's just going to be density. So it's mass per unit area times area. So I get rho, and the area of the whole thing is going to be the integral from c to d of x on the right minus x on the left dy. Just from what we've studied about the area between two curves. It's the right function minus the left function, because we're taking the larger x values and subtracting the smaller x values. So that's that formula. Then we can define the center of mass this way. You take, it's the opposite of what you would think, the moment about the y-axis, and you divide by the mass to get the x bar, the x coordinate of our center of mass. And for y bar, you take the moment about the x-axis and divide by the mass to get the center of mass. And if you have a constant density, and we're assuming that we do, This is also called the centroid of the region. Okay, so those are our formulas. If you want, you can just memorize those formulas and plug right into them. I don't recommend that at all. What I recommend instead is remembering that a moment about an axis is that mass times the distance to the axis, and the mass is density times the area. So if you understand the physics and you understand what a moment is, it's a mass times the distance to something, which is leading to a tendency to rotate about that something, then all of these formulas come naturally and they make a lot of sense. So those are our formulas for center of mass. Let's do an example. So here I've got x equals y squared. So that looks like this. And x equals y plus 2. So when y equals 0, x equals 2. When x equals 0, y would have to be negative 2. So I've got a line that looks like this. And this is my region. That right there. Now, since I've got this function on the left the whole time and this line on the right, it makes the most sense to integrate with respect to y. So I'm going to draw my rectangles horizontally. I'm going to try to figure out what that that y value is and what that y value is, so I know what my c and my d have to be. So the first thing we do on all of these is we graph the region, and we just did. And then when we look at the picture, we decide if we want to integrate with respect to x or y. If we're going from a left function to a right function, and we only have one function on the left the whole time and only one function on the right, we're going to draw horizontal rectangles. If we only have one top function the whole time and only one bottom function, we might draw our rectangles vertically. Now let's see what would happen here if we tried to integrate with respect to x. We could do it, but from this x value onto this x value, this is my top function and this is my bottom function. But right over here, the parabola is the top and the bottom function. So I'd have to do two integrals. This is going to make, or two integrals for the moment about the x-axis, two integrals for the moment about the y-axis, two integrals for the mass, and then I would have to put all those together to get the center of mass. This is going to be much easier. We're still going to have to do a lot of integrals, but we're not going to have to do twice as many integrals, because this function on the left is always on the left, and the function on the right, the line, is always on the right. So we graph the region. Then you're going to sketch representative rectangles. And you want to sketch representative rectangles that make the most sense to you. If you have those functions on the left and right the whole time, it makes sense to integrate with respect to y. If you have the same function on the top and the bottom the whole time, it makes sense to integrate with respect to x. If you have to do two integrals either way, or if you only have one integral either way, then you can go either way. It's up to you. So I've drawn my representative rectangles this way, and now I want to find the moments for that particular rectangle about the x and y axes. Actually, I think I want to find the mass first. Let's find the mass of the entire region, and then we will find the moments for that rectangle about the x and y axes. So mass is density, which is mass per unit area, times area. I don't even need the I. So we're going to get density times the integral from y equals c to y equals d of x on the right minus x on the left, and we're going to integrate with respect to y. Okay, so my right function and left function are pretty easy. X on the right is the line. X on the left is given by, it's that parabola. I've got x equals y squared on that parabola.
Now to figure out what my bounds are, I have to set this x value equal to this x value and solve for y. I want to find out where the x's are the same. That y value is that bound, or that bound. So I set x2 equal to x1 and solve for x. So I'm going to subtract y and 2 from both sides. See a nice simple quadratic equation. It's a nice easy one to factor. I need two numbers that multiply to give me -2 that add to -1. 2 and 1 will work if 2 is negative and 1 is positive. So it looks like this is 0 when y minus 2 is 0, so y equals 2, or when y plus 1 is 0, so y is -1. So that's -1, and that is 2. All right, so we're integrating from -1 to 2. That's easy enough. Oops, I don't even need that. I'm ready to antidifferentiate. So there's an implied 1 there. Add 1 to the exponent, divide by the new exponent. I've got a constant here. The antiderivative of a constant is a constant times y. Here, add 1 to the exponent, divide by the new exponent. Plug in -1 and 2 and subtract. So I've got rho times 1/2 times 2 squared plus 2 times 2 minus 1/3 times 2 to the 8, or 2 to the 3rd, which is 8. And then we're going to evaluate everything at -1 as well. There's not enough space, so I'll just do that below. So I have 1/2 times -1 squared plus 2 times -1 minus 1/3 times -1 cubed. All right, half of 4 is 2. That's 2 times 2 is 4. Then I've got minus 8 over 3. Then I'm subtracting a 1/2. And I'm subtracting a -2, so that's adding 2. And this is a positive 1/3, and I'm subtracting it. So that's 2 and 4 and 2 is 8. Subtracting 8 over 3 and 1 over 3, I'm subtracting 9 over 3, so I'm subtracting 3. And then I also need to subtract 1/2. So it looks like 5 minus 1/2, or 4.5. So that's 9 over 2 times rho, or 4.5 rho. Okay, that's our mass. All right, now we're ready to find the moments about the x and y axes for this particular rectangle. The moment about the x-axis is the mass times the distance to the x-axis. There's another problem down here. We don't have time to do it. I'll have to do that on a different video. Okay. Mass is density times area. And we're still multiplying by the distance to the x-axis. Area of this rectangle is x on the right minus x on the left times delta y. And the distance to the x-axis from the center of mass of that little rectangle to the x-axis here, that's just a y value. So this is just y sub I. I'm multiplying by that. That's not an x. Okay, so I've got x on the right, which is y sub I plus 2, minus x on the left, which is y sub I squared, multiplying by y sub I, multiplying by delta y. All right, so that's my moment about the x-axis. So my integral for the moment about the x-axis is rho, and then I've got y plus 2 minus y squared times y. We're integrating with respect to y, and we integrate from -1 to 2. And that's our right function minus left function, so that's going to come up again. First I distribute the y, and then I anti-differentiate. Add 1 to the exponent, divide by the new exponent. Bring the constant down.
add 1 to the exponent, divide by the new exponent. Those twos reduce. Bring the constant down. Add 1 to the exponent, divide by the new exponent, plug in -1 and 2 and subtract. So you've got rho times 1/3 times 2 cubed plus 2 squared minus 1/4 of 2 to the 4th. We're subtracting 1/3 times -1 cubed plus -1 squared minus 1/4 times -1 to the 4th. All right. Getting into the arithmetic now. I've got 8/3 plus 4. This is 16 divided by 4 is 4, so those reduce. And then I've got a minus 1/3, or that's a -1/3 times -1 is going to be positive 1/3. 1 times the -1 is -1. This is going to be a positive, no, -1/4, because that's going to be positive times a negative is going to be negative, times the negative is going to make it a positive. All right. So that is 8/3 plus 1/3 is 9/3, so that's 3. 3 minus 1 is 2, so I've got 2 1/4, which is 9/4 times rho, or 2 1/4 is 2.25 rho. Okay, it's a moment about the x-axis. Okay, let's do a moment about the y-axis now. So we got mass times the distance to the y-axis. And mass is density times area. And area we already found over here. It was this piece times delta y. Right function minus left function times delta y. It's the area of that little rectangle. Right minus left times the width. Then the distance to the y-axis is that distance there. It is an x value, but notice what it is. It's the average x value. It's the x value in between the x value on the right, or x value on the left, and the x value on the right. So the average x value is this. It's 1/2 of x on the right plus x on the left. And I have avoided using these formulas, but this was f sub I minus g sub y, and this is f sub y plus g sub y. That's my right minus left and right plus left. If you want, you could simplify the algebra. You're just going to end up with a minus b times a plus b is a squared. So it's going to be my x on the right squared minus b squared. X on the left squared times delta y. Now if you don't believe me, you can take that trinomial and multiply by that trinomial. Turns out you're going to get exactly the same thing here. So that's the moment for one piece. Moment about the y-axis for that one rectangle. And then the total moment about the y-axis is the limit as the number of rectangles goes to infinity of the sum of all the individual moments about the y-axis for all those rectangles. And that's going to define an integral. So I've got this rho over 2, and I'm integrating from -1 to 2. Those were my bounds for y for this particular problem. X on the right squared minus x on the left squared. And that's because I took the area, which had an f minus g in it, and an average distance, which had a 1/2 and an f plus g in it. And I multiplied those and I got this. So now let's do the algebra. Y plus 2 times y plus 2 requires a little distribution. Remember how this works? If I have a power raised to a power, I multiply the exponents. First times first is y squared. Outer times outer is 2y, inner times inner is another 2y. Last times last is 4. So we're going to add 1 to the exponent, divide by the new exponent. bring the 4 down. Add 1 to the exponent, divide by the new exponent, bring the 4 down. Antiderivative of a constant is a constant times that variable, of integration. Bring the negative down. Add 1 to the exponent, divide by the new exponent. Plug in -1 and 2 and subtract. It's a lot of work, but it's work that we can do. 4 divided by 2 is 2, and that's 2 squared. All right, that's evaluated at 2. Let's evaluate it at -1. Ooh. So I've got row over 2 times 8 over 3 plus 8 plus 8 minus 32 over 5. And I'm subtracting all of this, so I'm going to change the signs on these guys. That's a -1/3. I'm subtracting it, so it's going to be +1/3. That's a +2. Subtracting is going to make it a -2. -4 times a negative is going to make it a +4. That's a -1 times a -1/5, +1/5, but then we're subtracting it, so it's -1/5. Okay. That's 16. 20. 20 minus 2 is 18. 8 over 3 plus 1 over 3 is 9 over 3, so 3. So if 18 plus 3, that's 21. And I'm subtracting 33 over 5. So I can multiply this one by 5 over 5. I get 105 over 5 minus 33 over 5. It looks like I've got 72 over 5 times the row over 2. 2 goes into 72 36 times, so this is 36 row over 5. Or if you prefer, it's 7.2 times row. What was this again? Moment about the y-axis. Okay. So I found a moment about the x-axis, moment about the y-axis on the last page, and I've got the mass right here. And with those 3 pieces, I should be able to find the center of mass. Looking at this, the center of mass has to lie in the middle of that region somewhere. Let's see if we can find it. Center of mass is x bar, y bar. This moment about the y-axis over the total mass, and then the moment about the x-axis over the total mass. This is the center of mass or centroid, because watch what happens. I've got 7.2 times my density divided by 4.5 times my density. And since density is constant, those reduce. Moment about the x-axis was 2.25 row. And we're dividing by 4.5 row. So the rows reduce and we get this. Sounds like I'm talking about linear algebra. You know what row reducing is? Okay, that's for another class. All right. So I get 8 over 5 for my x-coordinate. And my y-coordinate is 1/2. So let's write those as decimals. It's a little bit easier to think about. So that's 1 3/5, so 1.6 and 0.5. Okay, let's look at our region. It says go to x equals 1.6. Y equals 1/2. So 1.6 and 1/2. And that is x bar, y bar. That is the balance point for that region. And I think that looks pretty good this time. Maybe I did a little bit better job with my graph, so it does look like all the mass, if it were evenly distributed around a region that looked like this, it might balance at that point. Okay, so quick review. If the density is constant, center of mass and centroid mean exactly the same thing. If my region looks like this, where x goes from a function on the right to a function on the left, the moments about the x-axis are given this way. Moments about the y-axis are given this way. I didn't put a box around it, but I should have. Oops, no, I did put a box around it. The box is down here. That's the moment about the y-axis. And that's my mass, density times area. And center of mass is just taking those moments and dividing by the mass, and we get the centroid, or the center of mass of the region. Now, you can memorize this if you want to, but the pictures will tell you what to do. You're always just going to draw a rectangle in there, and the moment about the x-axis is the area of that rectangle, which is x right minus x left times delta y, times that distance to the x-axis, which is y. So that gets me this formula. For the moment about the y-axis, I get the area, so x on the right minus x on the left, times the average x value, which is x on the right plus x on the left divided by 2, because I'm just taking the two x's and I'm averaging them. I add them together and divide by 2. And multiply those guys together. And then because a minus b times a plus b is a squared minus b squared, we get this nice little formula that looks like this. And density, or in mass, is just density times area. So it's just really an area with this extra row out front. Okay, so that's it for that. And I'll see you in the next video, guys.